In this video, we'll be looking at deriving the global stiffness matrix for a bar element that is arbitrarily oriented in the plane. We will start here by looking at an element that is arbitrarily oriented within the global plane xy, having global ordinates x and y, the horizontal and the vertical. And as you can see here, the element is oriented along the x prime axis, which makes an angle theta from the global x direction. So the local ordinates are x prime and y prime. So just to recall, we were able to write the element stiffness equations with respect to the local axis x prime, y prime, relating the element forces F1 prime and F2 prime to the element local displacements U1 prime and U2 prime in the earlier section, and we wrote that as F1 prime, F2 prime is equal to the element stiffness matrix multiplied by the element nodal displacements in the local coordinates. So that would be U1 prime and U2 prime. The stiffness matrix was AE over L multiplied by 1 minus 1 minus 1 and 1. And this was simplified in matrix form as F prime is equal to this K prime, the element stiffness matrix expressed with respect to the local axis multiplied by D prime. It is worth noting here that my F prime is a 2 by 1, my K prime is a 2 by 2, and my D prime is a 2 by 1. Now, our goal today is to be able to develop the element stiffness equations with respect to the global coordinates. So our goal is to be able to express the forces with respect to the global coordinates. So I'm writing it here as F, as they relate to the nodal displacement with respect to the global coordinates. So we want to evaluate this stiffness matrix with respect to the global axis that relates F to D. So we want to be able to relate global element forces F to global element nodal force displacements D. Now, I ought to mention here that as we start looking at the nodal displacements and the element forces, please note that because this is a bar element that is axially loaded, we were looking at displacements primarily along the local axis. When I start working in the global coordinates, I'm going to need to resolve the displacements, the local displacements and the local forces into components oriented along the global coordinates. So I'll be looking here at U1 prime is going to have two components, along the x direction and the y direction. So I'm going to get here u1x, and I'm going to get here a u1y. I'll be getting here a u2x and a u2y. Likewise, for the forces, my F1 prime is going to be resolved into two components, F1x and F1y. F2x prime is going to be resolved into an F2x and an F2y. So when I'm looking at element stiffness equations, I'll be looking at a relationship between F and D. And F now becomes a 4 by 1 because I'm going to have F1x, F1y, F2x, F2y as they relate to the global element nodal displacements, namely U1x, U2y. I'm sorry, this is U1y, U2x, and U2y. And these are going to be related via a global element stiffness matrix K. So when we look at the order of these matrices, we are looking at a 4 by 1, a 4 by 1, and therefore this element stiffness matrix is going to have to be a 4 by 4. And this is what we're going to be deriving in the next slide. Our first step here would be to relate the local nodal displacements to the global nodal displacement. So I'll be looking at my transformation equations that we derived earlier. So I can write u1 prime is equal to u1 cosine theta plus v1 sine theta. Also, I can write u2 prime as equal to u2 cosine theta plus v2 sine theta. Please note that I have one component in the prime direction that or the local direction, while I have two components with respect to the global direction. So if I want to write these two equations in matrix form to relate the nodal displacements to the global displacements, I would be writing it as u1 prime, u2 prime related to, now I have four components in the global direction. So I have u1, v1, u2, and v2. Clearly this is a 2 by 1, this is a 4 by 1. So we expect now some sort of a transformation matrix here that is gonna have to be a 2 by 4. And looking here at the elements for this transformation matrix, I have here a cosine theta, I have here a sine theta times v1, then I have a 0 and a 0, and for u2 prime have a 0 and a 0, then I have a cosine and a sine, and this here may be expressed as d prime equals to this T star transformation matrix multiplied by D, where again this D prime is a 2 by 1, this is a 2 by 4, and D is a 4 by 4. Similarly, we can relate F prime to F via the same transformation matrix T star. Now, if I look at my element stiffness equations, we had this F prime, which was a 2 by 1, is equal to the local element stiffness matrix K prime, which is a 2 by 2, multiplied by the local element nodal displacement D prime. Now I can replace F prime by T star times F prime, and I can replace D prime by T star D. And I'm sorry, this is T star F and not F prime. So we have T star F is equal to K prime times T star times D. Now, in order to solve for F as a function of T, we need to find the inverse of T star. And we want to make, in order to find the inverse, we want to make T star a square matrix to find its transpose, given that this is an orthogonal matrix. So we want to make T star a square matrix to find its inverse. Or its transpose since it is an orthogonal matrix. Once we do that, if I multiply by the transpose, I'm going to get that F is equal to T transpose multiplied by K prime multiplied by T multiplied by D. Now please note that here F is a 4 by 1, D is a 4 by 1, and when we make the T star matrix a square matrix, I'm going to end up with a 4 by 4. K prime is going to be a 4. I can also write K prime as a 4 by 4 and T as a 4 by 4. And if we look carefully at this equation, what we are trying to solve for is this element stiffness matrix with respect to the global coordinates K. So we get K here is equal to this T star multiplied by K prime multiplied by T. And I'm sorry that this is a transpose and not a star. So this is here the transpose, and this also here would be the transpose. So we have T transpose because I had to multiply by T transpose here to solve for F. So I get that K is equal to T transpose times K prime multiplied by T. Here we're going to expand on how we make the 2 by 4 transformation matrix a 4 by 4. So if I look at my local nodal displacements, I had the u1 prime and the u2 prime. I'm going to insert here a v1 prime and a v2 prime. And I'm going to relate this local nodal displacement to the global nodal displacements u1, v1, u2, v2. And we clearly know that this v1 prime and v2 prime are zeros. But if I apply my transformation, we had the cosine sine 0, 0. Then on the second row, we had a minus cosine, minus sine cosine 0 and 0. On the third row, now u2 is function of u2 prime is function of u2 and v2. So we have here cosine sine, and v2 prime is function of u2 v2. So we're going to have here a minus sine and a cosine, and we're going to add the zeros. So this here becomes the transformation matrix that is 4 by 4. So I can write here as d prime equal to a t multiplied by d, where clearly here this is a 4 by 1, a 4 by 4, and a 4 by 1. When similarly, we can write f prime a 4 by 1 equal to a transformation matrix that is 4 by 4 multiplied by f, which is a 4 by 1. Now when we relate the f prime to d prime, we had the stiffness matrix, and we can fill in some zeros here. So I can write the f prime a 4 by 1 equal to, and if you recall, our stiffness matrix was AE over L multiplied by, and this is going to be function of the local displacements, where I had u1 prime, v1 prime, u2 prime, v2 prime, the 4 by 1. Now on the first row here, I have a positive u1 prime AE times u1 prime. Then I don't have anything multiplied by v1 prime. Then I had a minus 1 and a 0. On the second row, we have simply zeros. On the third row, I would have a minus 1 and the 1 in the third column, and here we're going to have zeros, and the fourth row is going to be all zeros. So now to solve for k, with respect to the global axis, I have k is equal to the t transpose multiplied by this k prime, the 4 by 4, multiplied by t. When we do the math here, we are going to solve for this k with respect to the global axis. I'm going to get a cosine squared, cosine sine, sine squared, and this is going to be a symmetric matrix along the diagonal. So obviously you're going to have a CS here, and this is going to be repeated in the 4 quadrants with some sign changes. So here's going to be the same thing. I'm going to get it here. So I'm going to get cosine squared, cosine sine, sine squared. In this quadrant, I'm going to get some negative signs. So I'm going to get minus cosine squared minus cosine sine minus cosine sine and a minus sine squared. And this is the 4 by 4 stiffness matrix of a bar element that is arbitrarily oriented with respect to the global axis x and y. If we apply the symmetry, we are going to get here a minus c squared minus cs minus cs and a minus s squared. So this stiffness matrix, as you can see, the diagonal is all positive and we have symmetry along the diagonal. We can conclude that performing derivation yield the explicit stiffness matrix for a bar element arbitrarily oriented in the xy plane, looking here at the xk as a 4 by 4 expressed in terms of AEL and cosines and sine the angle theta between the x prime axis and the x axis. Please note that C and S represent cosine theta and sine theta respectively. When it is time to put together the total stiffness matrix, the element stiffness matrices with respect to the global axis may be summed together. So the total stiffness matrix would be equal to the sum of the global stiffness matrices of all elements summed from element 1 all the way to element n.